That is, notation is FDS, and the actual thing is F of R of t, magnitude of R prime of t, dt a to b. Then you go, this is the scalar, this is the notation. This is how it computes. The next part is the vector line integral. And for the vector line integral, you use f dot dr. And that's the notation. And then this is how you compute it. And so this is, again, notation. And that's the computation. Theorems. So when you start with the fundamental theorem of conservative fields, that is the you're saying that the integral of basically the gradient vector f dr is going to be equal to f evaluated at one endpoint and def, subtracting evaluated here minus evaluated there, right? So think about this. If you want to find the circulation, of a conservative field over a closed curve, right? What you get is basically, if this is contour integral, then you get f evaluated at a point. Beginning point and end point are going to be the same, right? Circulation means I start from here, I go all the way back there. So what is the value for that? I evaluate f at a point and then subtract from f evaluated at the same point. So this thing is nice because it tells you that the circulation of the conservative field is 0, right? And also you know that the curl of conservative field is 0. And so that's one thing. And then this helps me also if I have two different ways going from point A, B, C to E, F, G. I think I messed up that one, no? Yeah, D, E, F, D, E, F, D, E, F. And then another path like this. If I have two paths going from one point to another point, because the two paths basically, if this is C1 and this is C2, then C2 minus C1 makes a circulation. And so the line integral over C2 minus C1 of the conservative field is going to be 0. And that's why the conservative fields are path independent. So that's part of the story. The second part of the story is, we talked about the path independence. And then the second part is, well, now, what if that f is not equal to any gradient of f? What if curl of f is not 0? So that story comes in, again, we figure out if the curl of f is 0, the circulation is going to be going to be 0, but what if curl of f is not equal to 0? That's when the Stokes and Green's theorem come in, and they say, well, if that the curl of f is not 0, the circulation is not, it may or may not be 0, and you have to compute it by adding up all the circulations and the area sitting between them, and area inside it, basically. And so this is C of F dot ds. So it just, the right-hand side is just adding up all the little circulations, and that's the beauty of it.